Great. All right, so this is try two. We're actually recording this time. My name is Jake Weissman. I'll be teaching this installation of the network science introductory course as part of BVCN. And today we're going to talk about the graphical lasso or the glasso. Really we're going to talk about why correlation networks can sometimes give you results that aren't necessarily what you want. And so I'm going to share a whiteboard with you. I'm going to clear all the drawing noise. And so kind of what I'm going to start out with here is, because I'm going to really talk about this as a conceptual lesson. We're not going to talk about a lot of the math behind these methods. We will get into some code at the end, but I'm going to try to answer the question, why not correlation? And to start, let's imagine a scenario in which you have three species that I'm going to represent by X's. We're going to call them species A, species B, and species C. And let's imagine that species B is a predator of species A, so it eats it. And let's imagine that C maybe depends on some metabolite that A produces, if we're thinking about microbes, say. And so both B and C will have abundances that will have to track A because they require something that A is producing, right? And so if we think about what our data might look like in this scenario. And just so for future reference, this is reality, so that we know what this is, the real network that we're trying to infer. And so if we think about samples that are maybe over time or space or whatever sampling scheme you have chosen, we can think about how the abundances of these three species vary over samples, right? And in the last lesson, we used correlations between these abundances to build our network. And so let's imagine what the abundances might look like in this scenario. So let's think about A maybe having two peaks over time. Maybe you had two blooms. And then, yeah, and let's say, so that's A. Oh, wrong type of line. There we go. So that's A. And let's say B kind of tracks A very closely as a predator. And let's say C also tracks A relatively closely because it depends on A for some metabolite, right? So maybe it looks a little bit different. But B and C, I'm using the same type of line. Hopefully that's not too confusing. There's limited options here. And what you'll notice kind of is that, okay, so by design, we have that A and B are highly correlated over time, and we have that A and C are highly correlated over time. But as a byproduct of that, you also see that B and C end up being correlated over time or space or all of your samples. And so if we're going to infer our network based on correlations, right, so we have A, B, and C again. And we're going to say that this is the inferred network. So we're going to correctly get that A and B are linked. We're going to correctly get that A and C are linked, but we're going to end up with a third connection in our network, right? Because now we've kind of created this induced correlation between B and C. And you might think that, you know, this isn't really a big deal. Maybe it's you're interested in direct interactions, in which case that's fine. Maybe it's just one extra link, so who really cares? But if you're interested in things like network structure, you're going to get wildly different network structures. So as an example, let's think about a more complicated network that maybe looks something like this, right? And so this is still going to be a relatively simple network. It's going to be a pretty sparse network, and that's going to be important later, where we think about a network not having nearly as many links as it could have, right? So most of the pairwise combinations don't have a link between them here. And so if this is the true network, well, what's going to happen when we infer a network here? Well, basically, correlation is going to close all of the triangles in the network. So let's close all the triangles that we see here. So we'll draw a line here, and we'll draw a line here, right? We'll draw a line here, there, and there, right? And so already this network's looking extremely clumpy, right? If we were just to close all those triangles. And if you think that, well, that might also happen to things a couple nodes away, if you have these induced correlations, right? So maybe this guy and this guy are going to be connected. What you end up with is a cluster of nodes that are all basically all connected with all, that have they have no structural property kind of to these clumps, right? And so you get these clumpy networks where maybe you have a couple clumps that are highly interconnected with each other, but within those clumps, you don't really have any structure. And that's not because structure doesn't necessarily exist in the data, it's because correlations are unable to capture that type of relationship. And so what we're going to talk about is the graphical lasso. And I'm actually not going to talk about the mathematical machinery behind what this is, but basically what we've been asking so far is, are A and B correlated when we build our graphs? But what we really want to be asking is, are A and B correlated, controlling for C? And in kind of the most basic sense, the graphical lasso is going to allow you to do that control, right? And the way it does that is using something called a lasso regression. And so I've posted a link to a textbook in the lesson that you'll run through in the activity. But I'm not going to go over lasso regression. That's kind of beyond the scope of this lesson here. You're welcome to read about that, but it's essentially a variable selection method. So you're actually going to do a bunch of regressions where, say, you have A given B plus C plus D. These are, say, 4 species that have a bunch of samples with their abundances. And you want to predict A given B, the abundances of B, C, and D in any given sample. And then you'll do the same thing with B given A plus C plus D, and so on. And what the lasso is going to do is it's going to do variable selection, where it's going to drop out some of these variables. So maybe A ends up only being left with having D as a predictor, and B only ends up with having, say, C as a predictor or something like that, right? And so you start building up these connections. So we kind of the formalism is a little bit different here. And so lasso is going to allow us to drop out some of these variables. All right, so I'm going to share this lesson with you. So you should be able to download this from the GitHub. And this lesson is going to take you through clumpy correlation. So basically what I just showed you, and conceptually, there'll be a small example in R. It's going to talk a little bit about what the graphical lasso is and how you can think about it. It's going to point you towards a couple links. And then finally, I'm going to give you an example of how to use Speakeasy, which is a package that you actually saw in the last lesson, which implements the graphical lasso alongside a correction for compositional data, so amplicon data or anything where you have relative abundances, right? So it's important to both consider compositional data and issues about correlation versus partial correlation versus the graphical lasso. And so if you're not interested in relative abundance data, there's several other R packages that I point to that you can also use. And I've used them before. I'm happy to answer questions during office hours about some of those packages, especially the huge package. But Speakeasy is the one we're going to focus on. I'm going to use the same Terra Oceans data set as last time. It's going to be processed in exactly the same way. So this is that OTU table. And then there's some plotting functions and things just to make it consistent with the last lesson with how we visualize. But really, to run Speakeasy, it's a single line, right? It's just this line here. And it's relatively easy to break Speakeasy, so I break it kind of towards the end of the lesson. And so you should be careful about the warning messages you're getting during fitting. And then finally, I talk a little bit about, you don't really get a p-value out of this type of method, or generally when you're doing variable selection for individual connections, but you can get something sort of like a p-value if you really need a p-value. And so that's really going to be the whole lesson, and we'll go over that later in the week and run you through it. So that's all for now.